Hi, I'm Chidiogo Ono, and this is a supervised and unsupervised analysis on heart disease prediction. So, as an introduction, we will be using a heart failure data set. We have 12 columns, which are age, sex, chest pain type, resting blood pressure, cholesterol, fasting blood sugar, resting ECG, max heart rate, exercise angina, old peak, ST slope, and the target variable, heart disease. So we may already know some things such as that having an abnormally high cholesterol or having high maximum heart rate leads to an increased rate of heart failure. But by letting the computer do the thinking for us, we can discover more accurate methods of predicting our target variable of heart disease. Next, we begin with the planning and data prep. So I remove the null or missing values, and that leaves us with 918 observations across 12 columns. We have 410 zeros in the heart disease target variable, and that leaves us with 508 ones for a split of 44 to 56%. We encode our categorical variables for linear and logistic regression later, and we also scale our data set so that columns which may have been recorded at a higher order of magnitude don't thereby have a higher order of magnitude influence on the resulting models. And we'll be continuing with supervised and unsupervised methods. So which is better? With supervised methods, we can predict on heart disease. We can also do that with unsupervised methods, but in those cases, we'll be using these mostly for our feature selection because they are good at grouping, clustering, and associating the observations with one another. In a real world application, we would love to have perfect prediction for heart disease, but for medical research, it is very beneficial to know the groupings and the clusterings of observations. So both are good in this application. So looking at our k-means clustering, we have two plots which are defined for 2 and 3 groups. When we're looking at the top left, we see with the 2 plots that there's a very clear split down the middle, and there is more of an overlap when we look at 3 clusters. So I believe this is indicative of our target variable having 2 levels, which could explain why the split is so clear here. Although we do let the computer do the thinking for us, so we use the NBClust library to print out the statistics of the silhouette plot and the optimal number of clusters with the elbow method. And this tells us that we will be using 8. The silhouette plot says 8. The elbow method shows the elbows start to taper off around like 9 or 10, which is close to 8. So next we plot the k-means clustering with a 8 clusters defined, and it's very hard to interpret here. I believe what this is uh, caused by is the high dimensionality of the data. So perhaps if we could imagine 7, 8, 9 dimensions, we would be better able to tell a clear, well-defined bound on these clusters. But since it's projected onto a 2D plane, it's hard to interpret. And also we make the executive decision that since our target variable has 2 levels, we'll be going with 2. And we also see when showing the heat map of our correlations in the dendrogram that we have a light blue sort of here and another light blue shading here that could be indicative of 2 clusters as well. So we have clusters. What next? Option A, we can turn our clusters into variables and continue with those. Or option B, we can do variable selection to see if we can further reduce the dimensionality of our data before clustering again. And so to proceed, we'll next look at unsupervised and supervised feature selection, which is option B. So we start with the transpose method. with hierarchical clustering. So what that means is that we take all of the columns and turn those into rows. We turn the rows into columns, and then we can print a hierarchical clustering of our variables. So this one is showing the Manhattan distance and Ward D2 linkage. And we also have our maximum distance and single linkage. Here, note that we have 8 of our variables clustering out first, and the next 11 are in here. Uh, so what this means is that when we do start to do some feature selection, we may begin by removing these variables as their predictive significance may be captured by other variables in this same cluster. And we also include the Euclidean distance and complete linkage because it's a simple, theoretically simple, more simple to understand Euclidean distance and complete linkage. And with our cluster var library, we can also print the stability um, plot, which shows that 4 clusters is ideal. So for the feature selection, I write a function that removes variables of low height. So after we look at each step, we're going to be looking at the dendrograms, and then we're going to be removing variables. So for example, here we would start by removing perhaps the lowest height variable. So that's going to be resting ECG normal. These are our encoded variables, which is why we have so many of them instead of the 12 that we started with. Chest pain type ASY would be removed, or something that's very low, such as chest pain type NAP, whereas resting blood pressure, max heart rate, these ones clustered out first, so we would keep them. And we're also going to be comparing to a linear model on each step. So you'll see here that where is it? Here, we're going to be printing out the linear model of the data after we remove that function. And so when we print out the linear model, we can see the statistics and the um, p-values on the variables, which will give us a hint for which ones can be removed next. Although for the presentation, I did omit uh, all of those dendrograms because those would be a lot of steps to go over. At the end of the process, my final variable set is sex male, chest pain type ATA, chest pain type NAP, cholesterol, fasting blood pressure, max heart rate, old peak, ST slope down, and ST slope flat. So using this new set of variables, we got rid of all the other variables. So running k-means clustering for 2 clusters again results in this plot, although I do include this plot on the bottom right because on separate seeds, it did output looking like this. I thought it was interesting, but it doesn't have too much of a bearing on our results here. And we run the statistics again with our silhouette plot and our elbow method. So on this run, it does show that the optimal number of clusters goes up. And when we run the heat map for the correlation, we lose those 2 faint squares and we're left with a lot more smaller squares, smaller correlations of the variables. So we can also print the correlation of the matrix, or sorry, of the cluster to the heart disease column. So what that means is that before, when we're looking at our clusters here, initially I believed that the clusters may be indicating that these show a pretty good split for zeros and ones on the heart disease data. However, that is not quite the case. What we see is that there was only a 67% correlation, and so on with the additional clusters. You'll notice that with 8 clusters, the correlation goes down much lower. And that's to be expected because there's only 2 levels in heart disease, whereas when we have 8 clusters, there's 8 levels. And there's not much correlation between 2 levels and 8 levels. Um, and when we remove our variables, we do have less correlation, but it doesn't go down by that much between the before and the after when we're using 2 clusters. So we can see this as an improvement, where we're removing the degrees of freedom, um, and still retaining the correlation to our target variable. And at this moment, I was going to include the cluster into the data set as a variable, but I realized that that would introduce another degree of overfitting since that information is already innate to the observations in that data set. So we leave it out. And next, we move on to building our models. So first, we build our unsupervised model, which is going to be our Bayesian network. So we begin by running the cross-validation Bayesian network function uh, to see which of the algorithms might be the best according to its log loss. And then we score all of our algorithm results, and we see that the best one was Taboo, which is a score-based algorithm. And here's the resulting graph. And we also build our logistic regression and random forest models. So here in the top left, you'll see the logistic regression. We use this over linear regression because logistic regression is better for classification problems. And our random forest model is an ensemble tree that utilizes bagging. And in the bottom right, we'll see our Bayesian network with our Taboo algorithm. And to understand those numbers in the confusion matrix, we have a table here showing the accuracy of logistic regression, random forest, and Bayesian network Taboo. So our unsupervised method did do the worst of the three. This is expected since we're not using the target variable. For typically unsupervised methods do worse, but the Bayesian network does include the target right here, heart disease. Logistic regression is second, and random forest came out to the best results. So in conclusion, our final model was our random forest model. 56% of the observations are ones for heart disease. And our random forest has a sensitivity of 84%. So that means it correctly predicts 84% of our 56 observations. But is this model good enough to deploy at work? Well, we may choose to implement this model in a work environment, because 84% may be acceptable depending on the domain. So if we're saving lives, we would want to prioritize as many lives as possible. So 84% is a great number. However, we must also consider the false positives. So we don't want to prescribe chemotherapy to a patient who doesn't have cancer, and we don't want to conclude that open heart surgery is necessary for a patient who's just having some other sort of chest pain. For this reason, it's important to make sure that our specificity is also very high. Fortunately, our random forest model has a specificity of 93%. So that means of the 44% zeros in our target variable column, we can accurately predict 93% of the negative observations. And what this means is that going forwards with hyperparameter tuning, since our model is already good with the specificity, we have some wiggle room for prioritizing the sensitivity without losing too much on the other. So that has been my presentation. Thank you for watching.